In the previous few videos, we talked about Matlab's two-dimensional graphic capabilities. Right? We were making two-dimensional graphs, and we were manipulating those graphs and decorating those graphs using various Matlab functions. In this video, we're going to talk about three-dimensional graphs and three-dimensional plotting capabilities provided by Matlab. And you will see that it's also quite convenient, and it's also quite powerful. It's actually very powerful. It allows you to actually pretty much control almost everything inside of a three-dimensional environment, a three-dimensional scene. You can put anything into it, and then you can control the lighting, the color, the various aspects of a three-dimensional plot. So let's start by trying to create a script that's called a graph3d.m. And this is our script for 3D plotting, right? Or 3D graphics. So we'll start from the very basics, or start from the lines and points. Lines and points, right? When we're plotting lines and points in a two-dimensional graph, it's kind of easier for us to actually imagine how to actually position those lines and points on a two-dimensional plot, right? We have just the x and y axis. Once we have specified the x and y axis, we pretty much just we can just plot all those points with x and y coordinates, right? We can just position those points and the lines at the correct location, at the correct coordinates, horizontal and vertical coordinates. In three-dimensional plots, in three-dimensional graphics, we can also position points or lines in a three-dimensional coordinate system, right? So let's look at how we can construct some kind of a spiral in a three-dimensional setting, right? Some hex shape, t equals to link space. We're gonna use so t is gonna be a one-dimensional thing that goes from 0 to 2 times pi, right? And then say let's give like 200 points on that, right? A equals to 10, right? And then b equals to, and then c equals to. So what we're trying to do is to actually create a parametric representation of some kind of spiral shape. So x is going to be the x coordinates of those 200 points, basically. Right? We have 200 points on the t-axis. That's the parameter space, right? And then x is going to equal to b times cosine of t. And then y is going to equal to b times the sine of t. And then z is equal to c times the cosine of a times t. Right. And then let's just create a figure 1. Let's say figure 1, and then plot. When we're doing two-dimensional plot, the function name is called plot, right? But if we are trying to actually position those points at those x, y, z three-dimensional coordinates, we have to use different function that's called plot3, right? Again, we can look at the help page for plot3, right? But it's actually quite simple. Plot3 is a three-dimensional analog of plot, right? So x, y, and z are the three vectors of the same length, and then it's going to try to plot a line that's going to connect all the points that are positioned at those three-dimensional coordinates, right? So the first element in x is going to be the x coordinate of the first point. The first element in y is going to be the y coordinate for the first point and then the first element in z vector is going to be the z coordinate of the first point, right? And then the second element in x, y, and z are going to be the x and y and z coordinates for the second point, right? So here we have like 200 points, and their x and y and z coordinates have have all been computed by using these three equations. So all we have to do is to plot x, y, and z, and then the format specification, right? So suppose we want to plot as black dots connected by solid lines, right? Then that's going to be our sort of style specification, right? But x, y, and z are going to be the x, y, and z coordinates of the 200 points. So let's execute this code. Hold down Control key and press Enter. Then it's going to try to create this plot. Yeah, that's what this thing actually looks like, right? So maybe my description is not really accurate. It's not really some kind of hex. It's not some kind of spiral. It's some kind of ripple, right? Maybe I should say it's some kind of ripple, right? It looks like circle, right? So on the x and if you look straight down, if you take a top-down view, if you look straight down, then it's gonna be a circle, right? That's two. So the radius is like 1, right? So the center is at 0, the radius is at 1, right? So on the x and y coordinate, all the points display as some kind of circle, right? But if you look at the third dimension, you're gonna have this kind of ripple on it, right? You can have this kind of ripple on it. So if you want to rotate them, you rotate the curve, you can just click on this button, and then it's gonna allow you to rotate it, right? So what I'm gonna do is that I'm gonna put a box around the plot, so it's gonna be a three-dimensional box, and then I'm gonna say axis equal, right? So and then axis tight. Axis equal is gonna make sure that the scale for all the three axes x, y, z are identical. So one unit on the x-axis is gonna appear as the same length on y and z-axis, right? So one unit of length on the x-axis is going to be the same as one unit of length on y and z-axis. That's called axis equal. Axis tight is going to remove everything. It's going to remove all the white spaces around, right? So this way it's going to give me a very tight black box in which I can manipulate my figure, right? So that's pretty much just how we can plot lines and plot. So suppose you don't want to use a line to connect all the dots, you can just get rid of this dash, right? Or if you want to use dash line to connect all the dots, you can do that, right? And then if you don't want to use dot, you want to use stars, you can do that, right? So if you do that, then that's gonna be how the figure is gonna look like, right? So this is exactly as what's said in the help page, right? It's a three-dimensional analogy, analog of plot function. So how to use actually plot 3 is kind of a mirror image of how you actually use plot. It's exactly the same, except that you have to add one more axis now, one more vector. That's gonna store the z coordinates of all the points now, right? So that's how you can actually plot points and lines in three-dimensional space in Matlab. Now let's look at the surfaces, right? So how do we actually plot surfaces? So let's try to create some kind of a fake data so we can actually play with it, right? So x horizontal axis is going to be a link space from -3 to 3, and then we say 15 points, right? Y axis is going to be another link space from -3 to 13, and then with 17 points, right? And then that's going to be the range of our horizontal and vertical axis, right? But in order to actually make a surface, we have to sort of create a mesh based upon these one-dimensional vectors, right? A mesh is basically a two-dimensional thing, right? Two-dimensional matrix. And Matlab actually provides a very convenient function called mesh grid. Right, so x and y are basically just the one-dimensional vectors that's going to specify the x and y coordinates of every grid points, basically, right? So x is going to go from -3 to 3 with 15 points, right? That's a one-dimensional vector. Y is another one-dimensional vector. So basically, what you can think is that if you have a two-dimensional coordinate system, right, x and y, and then x is just this x vector is every element in this x vector is gonna create those markers on the x-axis, and then every element inside of the y vector, small y vector, is gonna create all those markers on the y-axis, and then all you have to do is to actually draw those lines, draw those grid lines, right? And then the intersections of all those grid lines are gonna be our mesh, right? Mesh nodes basically. And the mesh grid xy is exactly gonna do that, right? So it's gonna take these two one-dimensional vectors and then create a two-dimensional mesh. And then inside of this capital X, it's gonna store the x coordinates of every mesh point, which are the intersections of all those lines, horizontal and vertical lines, right? And then capital Y are gonna store the y coordinates of all those nodes, all those mesh points, right? And then once we have those x and y coordinates for every grid point on this two-dimensional mesh, we can try to compute a z function. Z gonna equal to, z is gonna depend upon the x and y, right, for every grid points. So x dot, it's an element-wise calculation, right? And then plus 3 times x dot get 2, subtract 2 times x plus 6, and then subtract 2 times y dot multiply x, and then dot get square, right? Plus y dot get square, subtract 2 times y, right? That's gonna be our z function. So the value of z is gonna be dependent upon both x and y, right? So for every grid points in our mesh, we're gonna do this calculation, right? Using its horizontal and vertical axis, using x and y axis, using its x and y coordinates to compute the z coordinate, right? So that's exactly the surface. So now let's try to make a plot of it. Let's create another figure, and then so the first function that we're going to try to use is called a mesh, right? That's a Matlab function for us to actually create 3D surface plots, but using mesh. How to use it is actually quite straightforward, right? So if you look at the manual page, it's just x, y, and z and c, right? X, y, and z. This is different from points, right? For points, x, y, and z are basically just the vectors, right? And they are just going to store the x and y and z coordinates of every point. But here, x, y, and z must be two-dimensional matrices, right? They have to be two-dimensional matrices. So usually you construct x and y by using a mesh grid, and then z is kind of computed from capital X and capital Y, right? And then you have some kind of color scale, right? But let's not make it too complicated now. Let's just look at the most basic usage, x, y, and z. Let's just look at that, right? So the figure is gonna look like that. So let me still do an axis equal. Axis normal. For some reason the display is kind of distorted, so let me it's probably a good idea to just decouple to undock the figure, right? Let me see if I can stock it in a better location. But anyway, it doesn't matter. Let's still go back to this code, and then what I'm gonna do is that I'm just gonna resize the window, resize the Matlab window, so that we can look at the figure and the code side by side. Right. So maybe that's a bit of arrangement, right, of all the different windows. So by default, it's gonna give. By default, it's the mesh function is gonna assign some kind of color according to the elevation of the points, right? Elevation of according to the z value, basically, right? So here you can sort of see that the nodes with a higher z value is gonna be colored to a it's gonna have a hotter color, right? And points with a lower z value is gonna have a colder color, right? Bluish, right? So that's like the default kind of a color scheme for visualizing this kind of a three-dimensional surface. Right? And if you actually let me create, maybe I should just create another figure and then do another mesh x, y, and z, and then let's get rid of this line. This line is not really necessary. But then let's add another command that's called hidden off. So what does it mean by hidden off? So for example, if you look at the graph from this particular angle, right? So this part of the surface, this angle, right? This corner is gonna automatically hide the stuff that's behind it, the surface that's behind it. So you won't be able to see through this particular corner, right? So that's called hidden. This part of the surface is hidden, right? Sometimes you don't want this kind of effect. You want to be able to actually see the entire surface, right? You want to see through the mesh, right? For now, the mesh is like opaque. You cannot see through it. But if you want to see through it, you just make sure that hidden off. You use hidden off to turn off the hiding, right? So now you can sort of see the differences between these two figures, right? So for this one, because the surface is opaque, so you cannot see through it. But here you are seeing through it, right? So everything is exposed to you, right? Even the mesh points or the nodes or the surface points or the mesh points that's kind of behind this particular corner are kind of visible to you, right? Maybe that's the effect that you want, but maybe that's not the effect that you want. So depending upon the specific application, you can decide for yourself if you want hidden to be on or off, right? It's purely problem dependent. So that's how you actually can use hidden off to turn this thing on and off. Right? It's a toggle. And then let's look at some kind of variations of mesh function. Let's look at figure 4, right? Mesh. The first variation is called mesh z, x, y, and z. Right. So what exactly is mesh z, right? Mesh z is it's just like a mesh, but it's gonna add some kind of a additional thing that's called a curtain, right? Or reference plane is drawn beneath, Um, so, um, but it's kind of difficult to explain. Let's just look at the effect, right? And that's sort of the curtain, or the user manual is talking about. It's giving you some kind of solid feel about the entire thing, right? So the surface you are plotting is still there, right? That's the surface, right? But underneath it, it's gonna add this kind of what they call the curtain, right? They call it curtain, right? But it makes the whole thing looks like um, makes the surface looks like some kind of a sculpture on top of a solid, right? So it gives you this kind of effect, right? But depending upon your particular application, maybe that's a good effect, right? You can decide for yourself, right? And that's called a mesh Z, right? And then when you actually looked at the menu page for mesh Z, you can sort of see another function that's called mesh C here, right? If I click on mesh C, it's gonna sort of tell us what mesh C is for. It's a combination of mesh and a contour plot, right? So it's gonna combine this mesh plot with contour plot. Again, let's look at what's gonna be the effect, right? Figure 5, mesh C, X, Y, and then Z. So that's figure 5, right? So this time you can sort of see their contour lines sort of located on the bottom of the figure, right? And this kind of effect doesn't exist for mesh Z plot or ordinary mesh plots, right? So you can sort of see the contours now, right? Right. Maybe Z limit minus 100 to 200. So this way maybe we can see the contours with better clarity, right? So the contour is located at this kind of horizontal plane. This located on the plane that's with z equals to 0, right? So it's located on the xy plane. So sometimes maybe it's kind of hard to see the contours because the surface is kind of so close to the xy plane, right? So maybe this is not a particularly good example for demonstrating this particular function, right? But you can sort of you sort of get the idea about what mesh C is gonna do, right? It's called a mesh contour, right? So that's all the kind of a mesh command or variations of the mesh command, right? And now let's look at another set of functions, another group of functions that's oriented towards creating the surface, right? So this is called a mesh, right? But let's look at another thing that's called a surf. So figure 6, surf x, y, and z, right? Surf is another very widely used command for plotting surfaces, right? Mesh is going to plot the surface as some kind of a mesh, right? But surf is going to try to actually put some instead of just drawing the mesh lines, it's going to try to put a color between those mesh lines. So it's going to give you some kind of solid feel, right? Right. So that's the effect of surf, right? You can still see the mesh lines, but the mesh lines are going to be just displayed as black lines, right? Here in the mesh plot, all the surface lines or the mesh lines are kind of colored according to the value of the nodes, right? But here all the all the mesh lines are just the black lines, but between those mesh lines, you're gonna see color patches. Those color patches, right? And the color is kind of determined by the value of the z value of the nodes, right? So so that's gonna give you this kind of a surface, right? It's no longer just the mesh lines, so you have color patches between those mesh lines. And that's a surf, and then surf also has its own variations, right? So the first one that we're going to look at is called surf AO. Right. Before we actually run it, let's just look at its manual page, right? Help surf AO. Right. It is the same as surf, except that it draws the surface with highlights from a light source, right? So it's gonna add some additional lighting effect, right? So it's gonna highlight, it's gonna have some kind of a perspective, it's gonna give you some kind of highlight, right? And then depending upon your graphic capability, if the graphics of your graphic card of your computer supports that kind of thing, it's this kind of highlights can be quite useful, right? Of course, it's got some kind of additional options, right? For example, it's got an option that's called a light, right? It's going to produce a colored light surface using the light object, right? And then that's going to be slightly different from the default lighting method, but you are going to have to specify some additional data to it, so to control how you want the light, what kind of light you want it to be, right? But let's just look at the default setting and then see if we can actually see some kind of effect, right? Yeah, you can sort of see a little bit of a difference, right? Where's the figure 7? Right. So some of the positions that's kind of close to the light source, you can imagine where the light source is located, right? Some of the locations that's sort of shine upon by the light source is gonna light up, right? So it's not gonna it's not gonna be as dark as previously, right? So you can imagine the light source might be located right here, right? It's sort of doing the kind of the lighting is actually going this way, so it's lighting up this particular value of the surface. So surf AO is gonna give you some kind of lighting control, right? So that's basically how you can actually use surf AO, right? But let's look at another command here. And this command is called shading, right? So what does shading actually mean, right? So you can sort of see here, shading is kind of when we were actually looking at the manual page for surf AO, shading was listed, right? See in the C also. So shading is a Matlab file. That sets the edge color and face color properties of all surface objects in the current axis, right? So it sets them to the correct values that depend upon whether the surface objects are representing meshes or surfaces. Right? So you have several options after shading, right? So if the default is a patch, I think, right? It's it's called the default is flat. I mean, the default is flat, right? It's gonna set the shading of the current graph to flat, which means what? Which means every patch that's between neighboring mesh lines are gonna have exactly the same color. Interp means interpolation. Interp means interpolation, right? So the shading on a patch is going to be interpolated based upon the values surrounding that particular patch, right? And then faceted, right? Oh, so faceted is actually the default, right? Flat is not. Flat is not. Faceted is actually the default, right? So what we are seeing here, so the default behavior here is sort of the patch, right? But let's look at the shading in terp and how it's going to change the view, right? So that's sort of the effect, right? You don't see the shading as individual patches anymore, individual color squares anymore, right? But look, gives you this kind of smooth feel, right? It gives you a very smooth surface, right? And then you don't see all the grid lines, all the mesh lines, all the black mesh lines have disappeared, right? So it's gonna give you a flat, a smooth surface. So maybe that's a good effect, right? And then the next thing that we'll try to actually adjust is called color map, right? When we did the two-dimensional graph, we looked at the color map before, right? We changed the color maps of the pie plots, right? Changed it from default to cool. But let's look at another color map that's called pink. It also comes with Matlab. It's a kind of a built-in color map, right? It's called pink. Pink is going to give you this kind of a color map, right? And it's going to make the surface looks more like a metallic surface, that kind of thing, right? It's pretty good looking, right? Makes it looks more natural, and when combined with the lighting, it really gives you a very kind of a realistic feel about the surface, right? So that's SurfKnown shading and color map, right? All three, the shading and color map actually is actually very useful. It's very useful for making your three-dimensional plot or surface plots looks very professional, right? And then let's look at one more variation of surf. It's called SurfKnown. Right. SurfKnown. Again, let's look at its manual page. Right. So it returns the components of the 3D surface normal for the surface with component x, y, and z. The normal is normalized to length 1. So what exactly is a normal, right? What exactly is a normal? If you actually think about each of the patches that's kind of a between neighboring, if you so if you actually pay attention to all the red sticks, right? Those red sticks are actually perpendicular to the local surface patch, right? If you sort of really look really sort of close, look really carefully, all those red sticks are kind of perpendicular to the curvature of the local surface, right? So if you look at the every patch or every node on the mesh, and try to actually draw a line that's kind of perpendicular to the local curvature of that node, then it's going to be the red segment, right? Sometimes you look, they don't look exactly like perpendicular. That's because your horizontal and vertical and the x, y, and z axis don't have the correct sort of ratio, don't have the correct scale, right? So on the x-axis, that's like 2 units, right? On the y-axis, that's like 5 units, and then on the z-axis, that's like 50 units, right? So the reason that at some locations they don't look perpendicular is because there's a difference in the scale of the axis, right? But the SurfKnown is gonna give you this kind of a effect, right? And then let's see if we can do some decoration on it, right? Let's still try another different map. Let's call it color map HSV, right? It's still a different color map, right? But let's just look at what this thing actually looks like. Okay, HSV, right? So maybe it's not a good color scale, right? Because the color of the red sticks kind of mixed together with the color of the surface, so makes the red sticks less visible, right? So maybe that's not exactly a good color map, right? So if you are interested in all those built-in color maps provided by Matlab, you can Google, right? But what I can actually do in this particular video is just to list some of the widely used color maps. One of them is called Jet, right? So if you change HSV to Jet, that's gonna give you another color map, right? So Jet is like the default color map, right? Jet, HSV, Hot. Hot is another one. Let me see. What's going? Okay, Hot. That's Hot. Jet, just Cool. We looked at the Cool when we were doing the pie plots, right? And then Spring, Summer, Autumn, Winter, Gray, Bone, Copper, Pink, and Lines, right? So all those are kind of built-in color maps that we can actually use. Of course, you don't have to put those commas over there. It's right. Let's just look at what's gonna be copper. What does copper look like? Right, maybe let me change the shading to interp also. Right. So that's what copper. What's the effect of copper that's actually giving you? Right. Okay, so those are some of the widely used color maps, right? Bone. You may feel strange about what bone is actually, what bone actually is, right? So this kind of thing is for this kind of color map sometimes is used for visualizing medical images, right? Suppose you have a CAT scan. Um, um, in fact, Matlab actually provides a default data, right? Let's load something. Let's load spine. So spine is actually a default data set, right? It's a medical image, right? It's a CAT scan of the spine, and then let's try to create some figure. Let's call it figure 17 or something, right? Doesn't matter. Doesn't matter what's actually, we skipped lots of figures in between, but doesn't really matter. And then we're gonna just display the data that's being loaded using this load spine, right? What's gonna be? We're gonna use the function that's called image, right? And then we change the color map to bone, right? So we haven't looked at the image before, right? We looked at the mesh, we looked at the surface, look at the surf, but we haven't looked at the image, right? Image is just for displaying a two-dimensional matrix. Here it's X, right? Displaying this two-dimensional two-dimensional matrix that's called X as some kind of color map, as a kind of some kind of bitmap. So every pixel on the screen is actually assigned a specific value, right? Based upon this the value that's inside of the X. It's basically a grayscale value actually. Let's just run it to see the effect. Right. So that's that's the CAT scan image, right, of a person's spine, basically, right? So um, so basically, you can imagine what X actually is, right? X is basically just a matrix with um, like a 350 to like a 400, 500, right? So let's look at the size of X. 367, 490, right? So it's got 367 rows and then 490 columns, right? Basically, it's a matrix, and then for every number inside of this particular matrix, it's assigned a particular value, and the value is basically just the grayscale, right? So if it's completely dark, it's completely black, then it probably has a value of 0 or something. And then if it is completely white, then it's going to have a value of 1 or something. And then if it's some kind of grayscale, some kind of color that's between 0 and 1, then it's going to give you this kind of gray color, right? And then image, the function image, is just going to sort of render this kind of a grayscale matrix onto a Matlab figure, right? And then for this particular data, color map bone seems to be very appropriate, right? It allows you to actually visualize this particular color map image, this bone image with very authentic looking X-ray view, right? It looks like an X-ray image, right? So talking about the default data sets, right? So spine is just one of those default data sets that comes with Matlab. That's like one of those example data sets, right? So inside of this particular sample data set, it's got some data, right? So let me clear all. Let me clear out everything that's inside of them, and then let me just run this piece of code, right? So it's got three things inside of it, right? X is just the matrix that we were actually looking at. Caption. Caption is like an empty array. It doesn't really store anything, right? And then map. Map is like 64 by 3 double. I'm not exactly sure, but maybe it's some kind of color map that comes with it, right? I don't really know. It's 64 rows, 3 columns, right? Maybe the 3 columns actually indicates red, blue, red, yellow, red, green, and blue, right? Maybe it's it allows you to actually display the image as some kind of colored image instead of grayscale image, right? Maybe that's the purpose of this map matrix, right? But let's look at another sample data set. That's called FluJet. It's also a data set that comes with Matlab. So if you purchase the Matlab, you have those two sample data sets. You actually have lots of sample data sets, right? But we are just looking at two of them in this particular example, right? And then let's do a figure 18 image X. But this time let's do a color map. Let's use jet, right? It's called FluJet. It's actually some kind of a numerical simulation of a fluid flow. It's kind of fluid dynamic simulation, right? And let's look at what this thing actually is gonna do. What this dataset actually looks like. It looks like that, right? Called FluJet. You are injecting some kind of fluid into some kind of background or some kind of container fluid, right? So that's going to display the pattern of the fluid, right? And then in this particular case, color map jet seems to be very appropriate, right? It's a good visualization, right? Okay, so that's like a an introduction to color map, how you can actually use color map for different purposes.